Good afternoon, everyone. I'm happy to be here and to present our research work on empowering smart cities through the convergence of artificial intelligence and virtual reality. So that's my PhD invitation. You can see here there are some two things might be worth noticing. First is the date, 2020, different year. Something happened, you already know. And I defended my thesis all by myself in a single room facing a screen. As you can see, we are Zoom meeting. So after I went back to China, I was put into a hotel for 2 full weeks. I was by myself in the hotel, have nothing to do. That's why I decided maybe I want to order some food just to enjoy the life in the hotel. So when I ordered, and this is the thing I noticed. And yeah, guilty as charged. I really ordered KFC, but I highly encourage you to try KFC in China. It's very different from the KFC in Switzerland. So after I get out of the hotel, I see robots everywhere. I mean, they're in the hotels, elevators, they are in the restaurant delivering food, they're in the shopping malls, guide people to the destination, and also even cleaning toilet. And that makes me wonder, I mean, we are really in this age of emerging of the robots technology. And traditionally, the urban automation technologies weren't there enough to really provide enough of intelligence and reliable for us. Thus, we need the robots to give us broader perspective of our relationship with them. But there are so many limitations. In this dynamic environment, it is difficult for the robots to really make quick decisions and also especially to comply with our social and safety rules. Thus, I want to study what's our relation between robots? What is the interaction between us and this nearly new family members of our society? Especially, I want to use artificial intelligence and virtual reality to study 3 different perspectives. How are the interactions between us? Are these interactions dynamic? And are these interactions adaptive? And are these interactions collective? Thus, the first one I want to concentrate is the dynamic part, because different from the laptop, which is supposedly kind of robotic and computer science technology, robots move. Their best advantage is they can be dynamic. And this is very crucial in evacuation situations. So traditional technology like signage already evolved a little bit through the time of improvement, and this traditional evacuation science already been adapted to intelligent science, but they cannot move, and that's the biggest benefit of the robots. They are dynamic, they can actually make decisions by their own. So we want to combine these two together, create our own movable, dynamic signage guidance robots, and also we want to test it using virtual reality. And a little bit demo of our study. So here you can see with those the real building. This is actually from a New York museum called Cooper Hewitt. We got their collaboration and approval to use this virtual reality environment to set their building on fire virtually. And so this is single player mode where you can just follow robots to find the fastest way to evacuate these burning places. And meanwhile, these robots can also be used with a group of people. So you can have the robots to guide a group of people, and moving all together, robots will take care of each of you and to form this kind of collective behavior to evacuate all together. Though it looks rather simple in the video, actually there are some quite mechanisms behind that. For example, the robots need to have this guidance mode, and the robots need to think what's their relationship between the people, the robot, and the exit. And also, most importantly, what kind of sign should I give to our audience? In addition, the robots need to think about the environment. For example, in these narrow door places, the people can only see a certain aspects in front of them. So the robot needs to be able to be visible for the audience and also remain relatively okay distance with their audience. Meanwhile, when the robots is facing a crowd, it gets even more complicated because first you can see with a crowd, one robot would not be enough. So we need multiple robots. So how do they collaborate? How do they work together? And also, usually within a group, you can see this crowd spontaneously form this leader and follower structure. So how do the robots see the leader? How do the robots really take care of the leader and the rest of the follower? And meanwhile, as you can see, since our robots only have one screen, the direction of the screen is also very crucial. Who do the robots face to? This information should be visible and displayable to all of our audience. So we solved all of these mechanisms and tested our system using two different groups. And we used our control group using signage technology, also developed them with Dirk together, also published before. We actually use this dynamic signs statically placed in the building, and they can directly automatically calculate the optimal route when a fire happens, and gives you the arrow changing animated display to your evacuees. Meanwhile, we use our robot group to just to test if this robot can actually behave as we want in the evacuation. And our result really gave us a very promising conclusion. So the robot group performed significantly better in success rate. That meaning if the crowd can actually all successfully evacuate in the fire. And also the robot performed significantly better in the single group in terms of using less time to evacuate. And also, meanwhile, the robots group actually traveled less distance in this evacuation. Meanwhile, we didn't find significant results into the multiple player group, naming with the crowd, probably because the group of the crowd actually have very small sample of number of participants. Meanwhile, also the group of the crowds is not really challenging enough for the task. So after we studied the dynamic aspects of the interaction, we realized that the robots in the fire situation, they are not really smart because the fires are static, the fire are predetermined, so the robots cannot make decisions if the fire location changes. So we ask ourselves, can we make the robots adaptive to different kind of tasks when the fire location changes? That's why we developed this adaptive reinforcement learning study to enhance the decision-making of the robots when facing dynamic fire scenarios. Specifically, we use this simulation structure where we can simulate the robots, the people, but also the fires. So in this simulation, the fire are also intelligent and also can make challenge tasks all by themselves. So here is the video. You can see on the left, these are the traditional evacuation scenario. If the robots just remember the exit and when a fire happens, and especially when the fire spread, the robot will make the wrong decision. But then on the left, on the right, if the robots can actually predict where do the fire grows, the robot can actually make a better decision to really find out the optimal route. So in our adversarial reinforcement learning, we make the fire also intelligent and try to keep coming up challenge tasks for the robots to solve. And the fire will be rewarded if they actually kill the robots, and the robots will be rewarded if they can solve the fire's challenge. So we have this kind of very amicable and competitive situation going on. Here we use a 3-floor building, have all different scenarios with doors and with stairs, and we have simplified robots and human representation in this framework, where the robots can see the difference between humans and the walls and the fire and the doors. So they have this sensing system where they can make decisions based on what they see. And here is a small demo about how the fire spread. You can see, just like in normal situation, the fire will keep spreading as time goes by, and the robots and the crowd will try to find the exit before it getting too spread it and block the whole exit. And meanwhile, this is the following behavior, which I mentioned before. So the robots will actually really identify the leaders and followers to see how they can guide a group of people all together. And when there are multiple scenarios, you can really see how the group really forms and make a collective decisions. And here in the reinforcement learning, we convert the environment into a neural network so that we can actually treat all this different environment as features to train our model. And the results showed that actually we have really promising results where the robots can actually solve most of the scenarios while the fire keep adding the difficulty of the challenge. So here are just some simulated results. You can see how the robots, the green dot, get the crowds, which are the yellow dots, to leave the fire as fast as possible. And just to validate our algorithms, we use the adversarial reinforcement learning we proposed and also compared with normal reinforcement learning without the intelligent fire. Meanwhile, we come up with a greedy algorithm and also the baseline without any intelligent decisions enhanced. So experiment results really demonstrate that as the difficulty increases, our algorithm outperforms others in terms of global health, meaning that how healthy they are when they evacuate, and also the success rate, namely how fast and how successful the evacuations are. So just to reflect a little bit, we come up with this semi-supervised adversarial reinforcement learning framework to have this generator, solver, evaluator structure. Namely here, the fire are the generators to keep coming up with difficult tasks, and the solvers are the robots to try to solve this task. And we also have a dynamic evaluator to tell the fire and the robots, are they doing okay, or are they doing good, or are they doing really wrongly? One thing we have noticed in this adversarial mechanism is that we cannot give the fire the reward function of just kill everyone, because in that case the fire will just be super crazy and spread everywhere and basically making the whole framework not really workable. So we come up with this mechanism that the fire's difficulties should increase, but with some reward going down if the task became too difficult. And it turns out to be really helpful for our evaluation and also the robot's behavior enhancement. So yeah, once again, the health level and also survival rate level proved our algorithm really works well. And also, especially, we're happy to see compared to traditional reinforcement learning, if we gave the robots more tasks, actually the robots will be more resilient. And last one, we want to start the collectiveness, because we also believe the mechanism should not just focus on the robots, but also should focus on us, the group, the crowd. Namely, we started the human-robot interaction in this collaborative navigation. So how do a group collaborate and navigate together? Here we have a robot to have 3 different modes, namely to identify the leaders of the group, as we mentioned before, to come up with mutual navigation paths. And also the robot should be able to tell a crowd when to stop and when to collaborate with each other to make the transportation more smooth. Meanwhile, the robot should also be able to tell the people who are lost where they should go and where they should be. So in here, we keep using our little cute robot, but giving more language informations to the robot. The robot right now can tell you, you want to keep following me, or you're doing to the wrong way, or you should turn back. And the robot will change the animation and the instructions based on the situation the crowds are and also the environments are. So as you can see in here, we really want to focus on the crowd robot's behavior in all different kind of scenario. That's why we come up with all 3 different kind of types of environment. So we have this straight line where just 2 group of people try to face each other and walk, but also we have this narrowed passage, which is very commonly used in crowd studies to see how 2 group of people to collaborate so that they will not be just blockage to each other. Meanwhile, we also added the crossroad and T-section, and also came up with two type of mazes to start a more broad and more flexible environment. So in the simple mazes, it's just very similar to the Manhattan structures, where you can just walk by going straight and turn left and right. Where we have the complex maze, this is literally a maze where you have to make turns and find your way out. So to study a crowd, it's a little bit harder than just starting single individuals. That's why we have to be prepared to actually put all the people together at the same room and let them do the same thing. So in this experiment, we collected all 16 different participants, put them into the same room, and gave them a synchronized software, allowing them to be virtually in the same environment online. So the whole procedure was carried with a within group design, and we gave the control group the map as a baseline, and in the experiment group, the robots will perform as we just described before. And once again, we found out that the robots actually behave really well as we expected to help a group of people to emerge collective behavior in terms of doing complex maze navigation. So when they are placed in complex environment, try to escape from a relatively large environment, the robots help the people to use less time to leave the scenario and also move less distance. So they need to, they can actually save more energies during the walk. Meanwhile, the robots will be very helpful when it is used in a simple environment. So they can help people to avoid the collisions. When the robots are present, the crowds will actually collapse and bump each other way less when there's a robot. So this comes to our conclusion. In this study, we focused on 3 different perspectives of human-robot interaction. The first, the dynamic part, we used the enhanced robot to improve the navigation efficiency and safety in complex evacuation scenarios. And the second one, we use the reinforcement learning to enable the robot to adapt their evacuation strategies, improving overall efficiency in this highly challenging and adaptable fire situation. And in the last one, we started the collectiveness and helped the robots to perform and operate a crowd with more efficient and more coordinations during evacuation. So that will be my presentation. Thank you so much for your time.